Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
This is the podcast where we search for the theories that are going to change the world. And part of that search involves philosophy. Today, we are tackling one of our favorite projects, which is quantum physics, through the lens of interpretations. What does the math and the experimentation actually tell us about the world? And how does the world of quantum mechanics map onto the world of everyday reality? How do the means by which we understand quantum mechanics map onto the rest of our approaches to reality? For the conversation today, we have Emily Adlam, who is a philosopher at Chapman University with a background in theoretical physics. And our conversation tries to understand how it is that we have failed to rectify ordinary reality with the world of quantum mechanics, and if there is a promising approach forward in the future, for which it does seem like there might be. But we have to reevaluate what it means to make a measurement in the first place, and what our failure to do so says about our theories as a whole, and how we go about constructing those theories.
If you like what we do at the podcast, then consider coming over to patreon.com/DemystifySci and signing up to support the podcast. Our lowest tier for that is just 75 cents a week, which we set specifically because even during hard economic times, most people have 75 cents a week to spare. And through the law of large numbers, that means that if we have enough patrons, we're going to be able to do all of the things that we want to turn this project into, which includes being able to record live interviews. It includes yearly live events. It includes being able to have more time to work on more books. We're almost done with our very first one. We have tons more planned. But in order to be able to do that and devote our full time to this project, we need your help. We do not want to have advertisers or sponsors or just weird schlocky things printed all over this podcast. And so if you like what we do, come over to patreon.com/DemystifySci. If you've already done that, there's a couple of other things that you can do. Number one is you can just share the podcast with somebody you know. You can like, comment, subscribe, do all of the things that as a talking head on YouTube I have to ask you for. And then if you have done all of that and you're still searching for something, then I have great news. We have started to make our own merch. So we have a couple of sweaters down in the description. Shiloh made one of the designs, I made the other design, and then we also have something that I am super proud of, which is our very first record. So we have a band called Secretary of Nature. This record is called Everything Is So Good Here, and it is 6 songs where we play all of the instruments, we write all of the words, we recorded it and mixed it right here in the studio, and I think that it's a pretty incredible record. I don't want to, toot our own horn or anything, but if you want to check it out, pick it up right now. It's called Everything Is So Good Here by Secretary of Nature.
There's a link in the description for that, and it really is the kind of music that I think is best enjoyed in the vinyl format. If you think vinyl records are stupid, you probably have no idea what I'm talking about, but there's something about just putting a record on and being stuck in that universe for 30 minutes or however long the side goes, flipping it, having a coherent experience on the other side. If you have a theory that you want to share with the world, consider checking out our monthly segment, Paradigm Drift. We're about to film the next one very soon. It will probably have occurred by the time this podcast goes out. So look forward to the next one in November. That date will be available on our website, DemystifySci.com, very, very soon. But I would love to see you there. Present your theory. Even if you don't get to present your theory, join in. Help other people develop their ideas. That is what it's all about. Otherwise, I hope you enjoy this conversation about how we make sense of the quantum world with Emily Adlam, and we'll see you next time.
The scientific revolution starts now.
DemystifySci podcast.
Let us see in the dark.
Perhaps we also live on some fringe of the internet where the measurement problem is taken to be an actual problem with the way we go about understanding these things. And
yeah, like this morning we were talking and Shiloh's like, I don't totally understand. Doesn't everyone agree that this is a serious problem? And it seems like, given that it's worth an entire book, I would assume that answer to that question is no, that most people don't realize that it's a problem.
Well, I mean, I think many people, there's certainly a split within, particularly the physics community, I think, in terms of some physicists are happy to take a sort of operational view to quantum theory and just regard it as a way to predict outcomes for experiments, and interpretation isn't important. But I think there are plenty of physicists and certainly philosophers who do regard it as a problem. I think, what I'm trying to argue in the book is not just to argue that it's a problem, but to argue that I think people are sometimes mistaken about perhaps not framing the problem in the right way or the most effective way. I think the problem is often framed as, we'd like to know what the ontology of quantum mechanics is. It's unsatisfying if we don't. And, I think that's true. But I think the point I was trying to make in the book is that these issues about the epistemology of the theory and like how we could actually come to know about these things seem to me like a more severe problem in terms of the sort of, in the sense that they undermine the like internal coherence of the theory, and they seem to raise some serious worries about whether the theory even makes sense.
Okay, so maybe we can back that up a bit and just talk about the state of the art when you arrived and what even got you thinking about this to the point that you end up writing an entire book about it. So, like, what did it look like? What were the issues as you saw them in your own personal experience that built to the point that you had something very projective to offer about the entire state of the art?
Yes. I mean, I think certainly as I came up through the field, my impression was that discussions of the measurement problem, I mean, in some ways felt like they were a little bit at an impasse, that there were sort of 3 or 4 main interpretations that people sort of had allegiances to, and people had preferences for various sort of reasons of almost of taste, I would say. And we weren't making progress because there was no sort of way to change people's sort of somewhat subjective judgments about which is the best interpretation, which we should move forward with. And I think certainly as I sort of started working on this, there are a number of interpretations that I had significant objections to for similar kinds of reasons, for the reason that I felt they didn't properly answer these questions that I had about the epistemology of the theory, about how are we supposed to have come to know about the things that we supposedly know in the terms of this theory. And so for that reason, it seems to me that once you frame the problem like that, the landscape looks quite different, because it's no longer the case that we have, 3, 4, 5 perfectly good solutions and we just have to choose. It seems to me that we don't have any good solutions, that all of them have pretty serious problems right now. And, there's some interesting new ideas coming out, but I think none of the existing solutions to me seem likely to work. So it's quite different.
Could we walk through a few of those? I would love to review those.
Do you think that it's worth setting up the problem a little bit more clearly first before we walk through the solutions of it?
Yeah, absolutely. Yeah, just for, not everybody in the audience is a huge quantum physics nerd like the rest of us. So maybe we can just give a scaffold for what the measurement problem is. And then, let's talk about some of these particular solutions and their failings.
Yeah, got it. So the measurement problem is basically arises from the fact that quantum mechanics seems to have 2 sort of distinct formalisms. We have the unitary formalism, which describes how systems behave when they elect to evolve independently of observers. And then we have this thing called wavefunction collapse, which is supposed to occur when a measurement takes place. In general, unitary evolution will put the system in a superposition of different classical states at the same time. So when you measure it, one of those states has to be chosen to be sort of selected as the outcome of the measurement, and that's what you see. And so those 2 formalisms are quite different from each other. One of them is linear and unitary. The other one is a sort of abrupt, irreversible change. And it's sort of quite difficult to see how they're supposed to fit together. It's difficult to understand what is the nature of the underlying reality that could make sense of that. If wavefunction collapse is a real process that really happens when you do a measurement, then it seems like we need some clearer definition of what is a measurement, what kind of physical interaction counts as a measurement, and if it's not a real process, then what is it and how can we understand that? So that's kind of the sort of standard understanding of it. The specific angle that I wanted to take on it here was in view of the fact that measurement is not just any old physical process. Measurement is a very sort of important category in terms of science and the way that we interact with scientific theories in the world. Measurement is the contact point between our experience and the world that we're trying to describe. So I think makes it a much more severe problem than if it's just some sort of thing in the environment that we don't understand. if you don't understand the nature of the process that connects you to the things you're trying to study, that means there's a really serious hole in the middle of your understanding of the theory. I think one of the important things that we sort of expect to happen when we do science is that we start out with various assumptions about our methods of inquiry and the reliability of those methods and how they're making contact with the world around us. And we expect that in the long term, those assumptions will be affirmed and that the theory will sort of say, yes, indeed, you are successfully making contact with the reality. And what seems to happen with several interpretations of quantum mechanics is that that does not come about. It seems like the theory is saying, these methods of inquiry are not reliable, something is going wrong. So that seems like an internal inconsistency to me. There's something that is quite a sort of serious and potentially fatal flaw for those kinds of approaches and something that we should be addressing.
Nice. Can I just clarify one thing about the presentation of the two formalisms? In the unitary formalism, do we not concern ourselves with wave function collapse or anything like that?
Yeah, the unitary formalism does not include wave function collapse. So that is just a system evolving when left to its own devices without being measured. So that is all very nice and linear and mathematically very pleasing, but it won't successfully describe a measurement.
So there's almost two realities happening that are perhaps at odds with one another.
There's definitely two different types of processes that seem to be involved. They're called process 1 and process 2 sometimes, but they're just very, very mathematically different. It seems quite hard to understand how they can make them fit together in a natural way.
Interesting. All right, so can we review some of the solutions that have been proposed over the years and see how they perhaps fall apart or contradict one another? And
so I mean, the approach that I think got me started on thinking in these terms is the many worlds interpretation or the Everett interpretation. So the solution that the Everett interpretation offers is to say there actually is no such thing as wave function collapse. When you perform a measurement, what happens is that all the branches of the wave function that were there before the measurement are still there after the measurement, and you yourself undergo a branching process, and different copies of you end up in each of the branches observing different things. So that is in many ways a very nice and satisfying solution. It avoids having to add anything to the theory. It's very sort of clean and simple. But it does, I think, come along with a variety of sort of interpretative problems and particularly, I think, epistemic problems. And I think criticism of the many worlds interpretation has sometimes focused on the thought that it's weird or that it's excessive to have all of these branches. But those are, I think, quite sort of subjective worries to have about it. That doesn't bother everyone. Whereas I think that there are also concerns to do with the sort of epistemology, which I think are much more serious and that we sort of do need to resolve if the theory is to be taken seriously as a possible option.
Yeah, because it seems like to me this is probably a really stupid idea, but it seems like if you have two copies or, I don't know, an infinite copies of the reality, like you have to multiply the matter somehow, like you have to get more material to have a new version of it over here. That seems like the main conceptual problem from where I'm sitting. But I'm curious if there's a formal name for that or what the epistemological issues with it are besides having to multiply reality, which requires you to create stuff out of nothing.
Yeah, I mean, I guess the worry you're expressing is that there's some kind of problem in terms of the conservation of matter or of energy or something like that. And I think the Everettians would respond that the correct way to understand those conservation principles is that they are sort of in-branch principles, and that we should expect that they will see what looks like conservation of matter and energy within each branch, but that in fact the laws of nature actually have this branching structure, and we just have to accept that. So that again is an objection that to me is a bit of a matter of taste. Some people think that is excessive and not reasonable. Other people are fine with that. I think the epistemic problems that I see, I think, are not just a matter of taste, but are a matter of internal consistency. I think the essential problem is that if your conception of measurement is that every time a measurement is performed, all of the outcomes occur and are observed by different people, it seems quite hard to understand what it could mean to assign probabilities to them other than just 1 or 0. Either it happens or it doesn't. Whereas, of course, quantum mechanics most of the content of quantum mechanics, empirically speaking, is in the probabilities that are assigned to measurement outcomes. In particular, how do we know that quantum mechanics is right? Well, we know because we have done a series of measurements, and we've looked at the relative frequencies of outcomes and seen that they match the predicted probabilities. So that seems to be a severe problem for the Everett interpretation, because if all of the outcomes are just always occurring, it seems like every possible sequence of outcomes will also always occur. And there's no particular reason to expect that the sequence of outcomes you have seen is going to be one that has high probability or high amplitude, or sort of is any way sort of special within the theory. So it seems to kind of break the connection that we need to have between observed relative frequencies and some structure that is important in the theory. So my worry there is that basically, if you believe the Everett interpretation, then it seems like you should also believe that quantum mechanics, the theory, has not really been empirically confirmed, because the methods of inquiry we've used to confirm it would not be reliable methods in an Everettian world. And of course, it doesn't make sense to believe an interpretation of a theory if it says the theory itself is not something you should believe. An interpretation should not undermine the theory it's supposed to be interpreting. So that I think is a sort of consistency issue that has to be addressed if we're going to take this seriously.
Yeah, it kind of reminds me vaguely of simulation theories, where you have, your solution to explaining physical reality doesn't, it sort of kicks the can down the road in some sense, right? If you're just like, well, and I think this is what you're getting at with the probability of anything happening is equally possible in this many world situation. Again, you're still left with, okay, but what about this branch that we're talking about? The one that we're concerned with, the one that we're all mutually experiencing here in this particular branch. We still have avoided really explaining the particular probabilistic outcomes that we do expect in each situation. And I see the same thing being a problem with people who are like, reality is a simulation. I'm like, okay, but it's a particular simulation at least, and we should worry about the rules that govern that simulation. And that's hopefully kind of what we mean when we say we're doing physics or science or something, that some collaborative project that everybody can work on together.
Yeah, and I think in order to meaningfully do any kind of physics, you have to start from the belief that the world has some kind of structure, and that structure is in a meaningful way being reflected in what we actually see. Whereas in the Everettian story, it seems like whatever you actually see is just a random quirk of which branch you happen to be in. There's no reason to expect it reflects any particular feature of the underlying reality. So it seems to sort of cut off the sort of main resource we have for learning about the world.
How seriously do people take the many worlds interpretation? Is it treated as a neat thought experiment that could technically produce a fitting solution for the problem, or is it actually treated as being a legitimate picture of reality?
I think it's taken very seriously. I think among those people who take the measurement problem seriously, the many worlds interpretation is definitely seen as being one of the main contenders, I would say. I think there's sort of three big interpretations, and many worlds is definitely one of them. It varies a little bit, I think, across different communities, sort of sociologically, and in terms of various people's backgrounds, there's different preferences for different interpretations. But certainly, many worlds is very well known, and I would say quite popular.
What were you going to ask, Shay?
I can't remember, but it just seems like this is an issue with probability in general, where it's easy to say, like, you look at the course of your life and you say, well, I was probably going to end up doing something similar to what I'm doing, but I could have done something different. Like, I could have been a doctor, I could have been a lawyer, I could have been in the army. Like, there's lots of different ways you probably could have happened. And to treat those paths of probability as genuine universes that did occur just seems like a massive jump. I wonder if there's any like philosophical grounding for that. Like, were the ancient Greeks considering these kinds of branching ideas for reality, or was it all metaphorical until very recently? Like, the fact that physicists are considering these as physical solutions seems perhaps unique.
Well, it just feels so sci-fi. Like, is
Very sci-fi.
Is fiction bleeding into science?
I actually think it's the other way around. I think that the recent interest in multiverses and in fiction and sci-fi has been strongly influenced by the many worlds interpretation, which has been around for a while, has been drawn on by various science fiction writers over the years. I think it is that science bleeding into sci-fi rather than the other way around.
Interesting, but it still seems like a pretty modern, at least 20th century approach to physical reality, to imagine these kinds of metaphysical solutions to physical problems. Is that fair?
To be fair, I feel like even the problem of reality being probabilistic as opposed to just deterministic is a 20th century problem as well in some ways.
When was Pearson?
Pearson was the statistician was like 1910s.
Really?
Yeah, it was super late.
Huh.
Yeah, I mean, I think the physicists at least would not want to regard the many worlds interpretation as being particularly metaphysical. I think it should be distinguished from the sort of philosophical form of modal realism, which says that every possible world in some sense exists somewhere out there. That's you could argue that there are some relations between that kind of idea and the many worlds interpretation, but the many worlds interpretation is usually read as in some sense, all of these worlds are really part of the same physical universe. They're all sort of physically connected. They could, in principle, interact with each other under very special circumstances. So it's not the case that we're sort of postulating this unknown multiverse of sort of other metaphysical worlds. It's supposed to be a single physical universe that has this branching structure. And that they want to say is just being read off the theory and the structure that we have quite straightforwardly there in the math. So in that sense, it's perhaps less strange and metaphysical than it sounds. It is sort of grounded, and this is the structure of the actual theory that seems to describe the physical world we have.
And so what are the ways in which it is criticized? Like if there's a sufficient contingent that looks at it and feels that it is a decent explanation for how to deal with the measurement problem, what are the ways in which it falls apart?
Yes, as I say, criticism has sometimes focused on weirdness or on just the ontological excess of it, or on, as we sort of discussed, issues relating to conservation, whether that's problematic. But certainly for me, the most significant concerns are those around the probability problem, around this issue of making sense of the probabilities. But even there, I would say, I think a lot of the discussion has seemed to focus on we need probabilities in order to understand, our everyday experience and the nature of, why it would make sense for us to make certain kinds of decisions in this world, and why it would make sense for us to live as we do, treating the future as sort of open and unknown and so on in this kind of world. And those are interesting and important, I think, but also to some extent somewhat subjective. You could feasibly just say, well, maybe we just shouldn't behave like that. Maybe that's what science is telling us. Again, I think for me, the important thing is to focus not just on we need to recover probability, but specifically on we need to recover a version of probability which can fit into the story we want to tell about the confirmation of the theory, to make sense of the idea that, yes, this theory does actually have empirical support, and that empirical support carries over and still makes sense in the many worlds context.
Interesting. All right. Well, maybe we'll circle back on this one eventually, but can we look at some other interpretations and their failings and their appeal?
Yeah. So another class of interpretations, which I think does or may encounter similar sorts of epistemic problems, what I would call the observer-dependent interpretations. And there's quite a wide range of these, and they don't necessarily all have this problem, but many of them seem to be moving in this direction. So these are the interpretations which say, roughly speaking, that quantum states, quantum outcomes, and facts about reality in general must be relativized to different observers. So that's kind of how they want to solve the measurement problem. They want to simply say that we have different observers, each having their own quantum description of the world relative to them, and those descriptions don't always have to agree. Sometimes they'll just end up saying different things, and that's okay because these are relative descriptions. So that includes, I think, most notably relational quantum mechanics, various sort of Copenhagen-ish interpretations, various perspectival interpretations, possibly what's known as cubism. All of them have in common this idea that this focus on the observer as sort of central object of the theory. And so for all of those, there are various different kinds of objections you could make. But again, the objection that I wanted to focus on is worries about how we can make sense of the practice of science in this context, specifically because if you take the story seriously and you really want to say all facts are relativized to observers or all physical facts are relativized to observers, the problem you seem to encounter is that there then can't be any facts about how one observer is related to another observer. So in particular, when you and I communicate, we would normally expect that some facts end up shared between them and I learn something about what you have experienced. Whereas it seems like in this kind of picture, that just can't be the case. There's just no fact of the matter about how our perspectives are related. So I can never learn anything about like what the world looks like from your point of view or what outcomes you have seen when you perform measurements and so on. So the worry there is that that seems to undermine the role that communication plays in science and in the practice of doing physics and arriving at theories quite generally. And more specifically, the whole point of relativizing things in these contexts was supposed to be to allow us to say that quantum mechanics is universal, that everybody sees quantum mechanics as right for everyone. But the theory then seems to undermine that position, because if I can only ever access facts relative to me and none relative to anyone else, it seems like I could never have any good reason to think that everybody else is seeing regularities that are consistent with quantum mechanics. So again, the sort of the central the means that we need to find out the information that's supposed to support the theory in the way that we've formulated it seems to be taken away by this interpretation.
It's fascinating to hear you talk about working on the problem in this way, because it seems like it touches something that Shaila and I have been circling around, which is that there's something about the nature of quantum mechanics and the way that it is interpreted that does not just remain in the realm of quantum mechanics.
Mm-hmm.
It seems to spread out to the rest of science, to the rest of the human project.
Mm-hmm.
And I think that you're the very first person that we've talked to that is really wrestling with it on that scale, because it's not just coming up with some explanation for what's happening inside of some experimental system.
Yeah. Mm-hmm.
You're literally saying that this has perhaps the widest implications of any interpretation for all of science, because literally what we do in science is we look at the world and we try to understand it.
Yeah.
And if we interpret the most fundamental version of that in a way that says that we cannot know anything, then we're totally screwed in every domain.
Yeah, no, I think that's a great observation. I think the thing about the measurement problem is that it's about measurement, it's about observation, and it's certainly not obvious prima facie that the only observations that are relevant to the problem are specific ones that physicists do in laboratories looking at Stern-Gerlach experiments or whatever it might be. In many of the interpretations, what we find is that what counts as an observation, a quantum observation or measurement, is just any interaction you have, any observation you make of the world is a quantum observation, in the sense that the world is quantum and these interactions are quantum in nature. So certainly there's at least a strong concern that whatever problems we have in understanding quantum measurement specifically are actually just problems that we have in understanding observation in general and the nature of our perspective on the world and how we're embedded in it. So, we don't know what the right solution is right now. So it might turn out in the long run that it all works out and none of this becomes important. But certainly with the way things stand, it does seem to me that there are problems in our understanding of the nature of our perspective and the nature of observation and existing in the physical reality, and that is sort of feeding into and back and forth from the measurement problem.
I have a bunch of questions downstream of this, but before we start to veer off, can we get the third interpretation on the table, or do you
Let's
have a
exhaust
question?
as many as we can, yeah.
Mm-hmm.
Yeah, because I have a tendency of just wandering away into the bushes, and so
I have a comment though. The observer dependent thing is interesting. I think we see it in other parts of society too, because everybody's got that crazy uncle who's like, "There's no facts left anymore. Nothing makes sense. Like, you can't trust anything that anybody says because everybody's just saying opinions." And it's like there is some truth to that. There is some truth to that, but at the same time, you have to be able to compile and concatenate these perspectives in such a way that you are able to model a coherent reality. I mean, science doesn't recapitulate reality, it models reality based on some parameters that you specify. It wouldn't be a model if it was just perfect in reality. So I think it reflects, again, something that's happening in our society in general. This whole quantum world is in some sense analogous to these bigger problems that we're facing. It's hard for me to not see that.
Yeah, I think in recent philosophy of science, and particularly feminist epistemology, there's been a lot of emphasis on the role of perspectives and standpoints, and the fact that we all come to science from a particular standpoint, and that is, of course, not something that we can eliminate. We can't not have a perspective, but at the same time, there's also been emphasis on the importance of communication and intersubjectivity and working as a community, and the ways in which that can help address some of these problems and get us towards a more unified, perhaps more less biased picture of the world. And I think that emphasis on the role of communication and intersubjectivity in science is important and really, really telling. But one of my worries about these interpretations is precisely that they seem to undermine that really central process and way in which we can arrive at some kind of meaningful mutual understanding by these sort of processes of interaction.
Coherence, yeah. Okay, let's look at a few more of these. Do you have another?
No, I want to go to the other ones because I feel like as a whole, they point to some really incredible feature of quantum physics that I think we haven't had a chance to talk about on the podcast explicitly, which is why it's so central to literally the way that normal people think about the world. The ideas of quantum physics have filtered so fully into society that you see people that are informed by the philosophical principles of it without even being cognizant that they are operating in their own minds. And that's I want to get there, but I want to get through this last measurement issue.
Yeah, so the last sort of class of interpretations that I talked about is what we might call the primitive ontology interpretations. So these are the ones that are trying to take, I guess, a somewhat more traditional approach to interpretation. What they want to do is identify some set of like well-defined, somewhat classical in nature beables or variables, and be able to tell a story which fully explains all of the quantum observations using just these sort of classical-ish variables. So one particularly well-known version of that is the de Broglie-Bohm interpretation, which, at least in the non-relativistic regime, tells us that the world is made up out of particles, and they're essentially classical. They travel along well-defined trajectories in space-time. They always have well-defined positions, but they are guided by an equation which incorporates the quantum wave function. So that is supposed to be how we reproduce the quantum behavior. We have all these classical behaviors, but they're traveling along sometimes quite strange trajectories because of the way the quantum wave function is guiding them. So that is in many ways a nice solution. In particular, it does seem to avoid the kind of epistemic worries that I've been raising, because in this picture, there's one well-defined world made up out of these particles. We all exist within that same world. We all have access to these same particles. So we don't have these problems about probability. We don't have these problems about communication. All of that stuff goes away. But the problem we do have is that it's not clear that this approach can be extended to quantum field theory and to relativistic quantum mechanics in any straightforward way. There are sort of versions of it which will work for some regimes of quantum field theory, but there does not yet seem to be anything which will just unilaterally reproduce all of quantum field theory. And there are some reasons to think that it's quite unlikely that anything of this kind would reproduce all of quantum field theory. And maybe that will turn out to be wrong, and some genius will come along and figure out how to do it. But right now, there's definitely reasons to be worried about that. And more generally, there are other interpretations in this class. The sort of spontaneous collapse interpretations also fall into this class. All of those sorts of like relatively classical things, and all of them, I think, face a similar kind of problem in that because they are necessarily changing the mathematical formalism of quantum mechanics and adding something quite significant to it, they then are very difficult to extend beyond the sort of straightforward non-relativistic regime. And to my knowledge, I don't think any of them has yet been successfully extended in a way that will just straightforwardly reproduce all of QFT. So insofar as QFT is also a very successful theory and it's part of quantum mechanics, it seems to me essential that the correct interpretation should, in the long run, be able to reproduce QFT too. So that provides some reason, I think, to be worried about this sort of general class of interpretations.
Do you think that's just a lack of attention, or is that a serious roadblock? Like, people just haven't been working on it as much as they've been working on some of these other projects for as long. Is it just a matter of time, or do you think that there's something seriously problematic about applying pilot wave theory to some of the details?
Yes, it's certainly possible that it is just a matter of time, and someone will eventually have a great insight into how to do it. That said, I think there are some reasons to think it's going to be very difficult and maybe not possible. David Wallace has a nice argument around this, noting essentially that if you are a reductionist, if you think that everything that happens at larger scales depends on what happens at smaller scales, then you're going to naturally assume that if you're adding something like de Broglie particles or whatever it might be into your ontology, you're going to have to do that at the smallest possible scales, and then you're going to have a consistent story about how it transforms as we move up through the scales to get to the picture that we the world that we as we experience it. And the worry he raises is that in QFT specifically, the transformations involved, the coarse graining transformations, work in a very sort of complicated way. The connection between larger scales and small scales is quite messy and indirect, and doesn't sort of transform in any straightforward way. So the worry here is that anything you added in to your theory at very small scales, which looks like reasonably simple and the kind of thing you would want to have in your fundamental ontology, is going to be transformed by these transformations into something like very messy and funny looking at large scales, in a way that is probably not going to reproduce the behavior that you wanted, the simple Bohmian particles or the wave function collapses. In particular, I think it's a bit difficult to see how you could add something in at very fundamental scales and then have it emerging at much higher scales in a way that singles out or ends up existing in just one branch of the wave function, which is what you need to solve the measurement problem. That because the branching structure that is relevant there sort of doesn't even really exist at very small scales. It emerges a bit higher up. So it's, again, not impossible, but certainly doesn't seem straightforward to see how you could get things to emerge in the right way.
Do the other interpretations that we reviewed so far, they suffer less from this scaling issue? They don't compound their errors in the same way?
Yeah, so the many worlds interpretation, for example, one of its main strengths is the fact that it doesn't change any of the math. It doesn't add anything to the mathematical formalism. It just leaves the theory as it is. So therefore, in some sense, the many worlds interpretation just by default extends to any regime where quantum mechanics can be applied, because it just is quantum mechanics, mathematically speaking. That's perhaps a slight oversimplification, that you might have some specific worries about what to say about the ontology in certain regimes, or can you sort of tell the right story about the branching structure? So maybe it's not quite as simple as the Everettians would want to say, but certainly because they're not adding anything, they're not putting any new math in the theory, they just by default have a much simpler problem than someone who's adding something like that.
I see. Yeah, I guess I just don't understand what the Bohmians are adding mathematically to the puzzle. I guess they have this whole other series of particles that are riding on these waves, so they can take the waves as they are, right? I assume they're using the quantum mechanical wave functions that everybody else is using, but now they have this physical material system they have to paste over top of it, and that's where the problems arrive, is trying to transfer those into larger and larger scale behaviors.
Yeah, exactly. So the Bohmian wave function is just going to evolve in the same way as the Everettian wave function. So that part should be fine. But the particles you have to put into the theory in some way. And as Wallace says, if you are a reductionist, it seems natural to think that you should be putting them in at very small scales and not at sort of the experimental scales that we're most familiar with. So therefore, you're going to have some way of doing a sensible transformation from the very small scales to the much larger scales, and that's the part that doesn't seem obvious.
So in terms of measurements, just in general, it seems fairly straightforward that if you have a system that is undergoing some kind of complex harmonic behavior, which does seem to be what the wave function is describing, because you can see that there's a two-dimensional version of the wave function that shows up on these Chladni plates, the wave function is also describing spherical harmonics, and so it does seem like it's talking about some kind.
For the electron, the wave function for the electron.
Yeah. And so it does seem like it's describing some kind of harmonic system. And from everything that I know about macro scale harmonic systems, it's that if you interact with them, you destroy their ability to vibrate harmonically. And so is there some reason why that just doesn't work in terms of quantum mechanics, to say that you have a system that is delicately balanced in terms of its behavior, and then you touch it and you destroy it?
Yes. So, I mean, in some sense, that is true in quantum mechanics. So, in particular, we have this phenomenon called decoherence, which is about the way in which wave functions evolve as you reach macroscopic scales and have monitoring by the external environment. And what we do find is that indeed decoherence typically has the effect of diagonalizing the density matrix. So essentially all the sort of coherences go away. The different branches of the wave function stop interacting with each other. In some ways, they sort of stop acting like a wave in that sense. So that it is certainly relevant to the measurement problem. That does seem to mean that sort of by default, as you approach the macroscopic regime, the wave function kind of separates out into separate, well-defined posi-classical worlds. And that is, for example, very important for the Everettian story, because they want to say, once we get to appropriate macroscopic regimes, all these things become separate and stop interacting, and we have distinct worlds. It doesn't solve the problem by itself, because although the branches of the wave function do separate out, and they're all still there, you don't end up with one branch of the wave function. You just end up with all of them sort of separate, no longer interacting. So that still by itself doesn't seem to explain why it is that when I do a measurement, I get like just one classical outcome. It explains why I get a classical outcome, but it doesn't explain how it comes about that there's just one, or how that just one outcome is selected. So although I think you're right to highlight the fact that things behave differently in macroscopic regimes, and that's certainly going to be important to the solution, it doesn't seem to me that by itself decoherence is going to be enough.
Well, in the sense of like trying to predict why so you have something that's behaving in this quantum way, and then you measure it and you get some probabilistic outcome of the measurements.
Yeah.
I mean, doesn't the probabilistic outcome of the measurements just tell you about the various states that system is in, and the amount of time that the system spends in each type of state, and that's what informs the likelihood of you collapsing it into a classical state, because the state that it's in when you measure it is what determines the outcome. And so the wave function is this like smearing of things across a time interval, which in reality are sort of happening discreetly, but at a rate that is so fast that you can't detect. Is that crazy?
I mean, I think that kind of story is potentially a nice way to think about it if you think of yourself as being like separate from and external to the system you're describing. So if I'm a classical system and I'm looking at some oscillating quantum system and I'm measuring it and I'm seeing some outcome which is giving me information about the oscillations or something like that. That's all fine as long as you are willing to treat the observer as outside and not themselves quantum. But I think sort of at the heart of the measurement problem is the thought that observers are part of the world too. Observers are also quantum systems, and therefore, I should be able to describe what's happening when the observer interacts with the system within the quantum formalism without introducing a kind of external classical intervention or external classical sort of framework that is going to model what is happening there. So once you start trying to model the observer as a quantum system as well, that's when you end up with this problem that it seems like all the branches are just still there and there's no way to get rid of them within a sort of purely quantum formalism.
I want to work towards your ontological solution for this, and I don't want to step. I know you have more questions too, but there's one interpretation that we skipped that I thought maybe I'd get you to weigh in on, which is our dear friend Carver Mead's transactional interpretation of quantum mechanics, which in some sense brings in Feynman's conception of reality to some extent. Where does that fit into this map of possibilities?
Yeah, the transactional interpretation, I would say, falls into the third category. It's not quite a primitive ontology approach, but it is certainly adding something to the theory, and it certainly does seem to intend to deliver us a single well-defined world in which if we all share and we all have the same information. I think the transactional interpretation is very interesting. I think the concern I have about it is that in order to be consistent, in order to avoid the sort of closed causal loop type problems that Maudlin, for example, has written about in the context of the transactional interpretation, it seems like you have to move away from the sort of literal type of translation that it seemed what was being originally posited, and towards a less literal story in which what we're really doing is thinking about the whole transaction as being a sort of atemporal process that happens at once. And I'm very interested in that kind of atemporal all at once approach to quantum mechanics, to physics more generally, but I find it a bit unnatural to focus that on a sort of single transaction. I think that once you're moving to this like all at once atemporal story, it seems like that all at once atemporal story should just apply to the whole of history, and we should have some model which looks at all of history at once rather than at sort of focusing on a single transaction in that way. So I think that's a very interesting direction of inquiry. I think I'd like to see the scope of that story expanded a bit more to be able to embed the transaction consistently in a story about all of history.
Yeah, I actually I talked with Carver and Kramer a bit about this because
And Kastner.
And I also had a strange reaction to this idea that the atoms should reach back in time and talk to the atoms that they're going to be partnering with for this dissipative process, when one atom resonates another and so forth. But I pointed out, Nastia pointed out, we pointed out that in some sense, spatial participation is congruent with temporal participation. In other words, if the atoms are connected physically through some extension to begin with, then it's feasible that their shared surfaces could participate in the event, and it sort of solves the problem of smearing out this weird time travel business without having to do anything remarkable. And we didn't really get much farther than or formalize it anyway, but all three of the transactionalists that we've gotten to know over the years seem to think that was possible, but their responses ranged from "Wow, that's a cool idea" to "I don't see what it gives us." So there's that.
Yeah, no, I think that's a cool idea too. I definitely think that the transactional interpretation does get something right, because I do think some kind of like atemporal all at once style story is very strongly indicated by many things that we know. So I'm not totally confident that the transactional interpretation is the right way to think about that. I mean, in particular, I think the transactional interpretation seems quite focused on trying to sort of explain the occurrence of an individual outcome in a way that perhaps is just not my main concern. I'm perfectly happy for outcomes to just be sort of indeterministic. I don't know if I feel like we need a more detailed story than that. So for that reason, I'm not sure that the transactional interpretation as it stands is like completely addressing the kinds of problems that I find the most pressing. But I do think that the approach that they are taking is really promising, and I'd like to see that, as I say, perhaps the scope widened a little bit.
Yeah, I just think the coolest part for me is just that, light involves two atoms, perhaps. Like, things start to make a little more sense when you bring when you have two. Like, you treat it as a conversation as opposed to just this magic bowling ball shot off into God knows where. All right, sorry, you were working out we're working towards Emily's epistemological revision here, but you were working out something with respect to the measurement problem itself.
Pardon the interruption, but I have to ask you for a favor. If you are listening to this podcast and you like what you hear and you want to support us, then come over to patreon.com/DemystifySci. We do not want to sell you pills and supplements and weird tchotchkes. We want this to be free for everybody and not contaminated by this just endless stream of consumerist nonsense. The ideas stand for themselves, but in order to make that a reality, we need your help. So come on over to patreon.com/DemystifySci and sign up to support us for as little as 75 cents a week. I'll see you there. So we're talking about measurement. We're talking about the way that interacting with quantum systems changes them and how we understand that. Is there a problem with the fact that we don't totally understand what the quantum system is? Because the wave function very discreetly does not describe physical reality. It describes some kind of higher dimensional complex state. And so is the fact that there's even a measurement problem to begin with partially due to the fact that we don't have a really good model of the thing that we're measuring, and so we have a hard time coming to conclusions about that?
Yes, I mean, I think that to some degree is going to vary across different interpretations. Some interpretations are going to say that the wave function does describe physical reality, that reality just is the wave function, and that the physical objects that we're familiar with just emerge out of the wave function in some appropriate regime, and that's all there is to say about it. Other approaches are going to take a more or less opposite viewpoint and say that reality is in fact made out of physical systems, and the wave function is just a convenient way of describing certain facts about how they interact with each other, and so really the physical systems are what matters, and physical systems are presumably just classical systems or something. And then other interpretations are going to say something a bit more in between, where in some sense both the wave function and the system per se need to be regarded as elements of reality by themselves. So I think there's a sort of wide spectrum of approaches across all of these interpretations in terms of what we should say about what is really there and what is physical and what is not.
Does it answer your question?
I mean, I think that to some degree, I wonder if there's a clear model for why this is so difficult to pin down. Like something that we've been playing with a lot is the idea that systems that you can look at are relatively easy to conceptualize. And
Yeah.
there's a moment in the early 20th century where we have some information about heredity. It's like Mendel has done his experiment with the peas. He's mapped out the likelihoods that you're going to get, short, wrinkly peas with yellow flowers versus tall, smooth peas or whatever. But we don't have a medium for inheritance. And yet we also have microscopes, and we have people that are working out the first biochemistry methods. And so you take the fact that you can look at a cell and you can say, hey, there's this really weird chunk of the cell that appears to be doing something as it's turning into two cells. And then you have this guy who goes to a hospital and he collects all these bandages that are soaked in pus from wounds, and he isolates the material and he figures out that it's really phosphate enriched. And he's like, well, white blood cells are mostly this substance, and so maybe this substance is the thing that's so you have this gradual creep towards a physical system.
Yeah.
That
Because the observation has gotten really sophisticated over the course of the 20th century, essentially, right? Like it could have, if they hadn't developed the microscope and X-ray diffraction and whatever else, the phosphate detection mechanism, they might have just been left with a probabilistic map of heredity.
And they tried to do that, which is crazy. So Shiloh asked about Pearson. And the biostatisticians, the biometricians at the turn of the century basically had this mindset of, it doesn't matter what it's made out of. We can parameterize inheritance to a degree that we can tell you what's going to happen within some realm of probability. And that should be enough for us. And we can just have this very mathematical biology and we shall move forward and it's going to be beautiful. And yet, because we had microscopes, there was people who would stand around and say, oh, that's fine, but there's actually something down there. And I feel like quantum physics just doesn't have that immediacy. You cannot see it in a microscope. You cannot actually view it. And so we're stuck with the fact that we're just almost in a dream world where we recognize that something is happening down there. But what it is just a canvas on which to project our wildest imaginations.
Yeah, and I do think that, I think as we move into, regimes which are further and further from our everyday experience of the world, it is, it just becomes less and less likely that whatever is there is going to be a thing that we can straightforwardly conceptualize, based on our brains being designed to function in this sort of classical regime. I do think that even though if there's a point where beyond which we shouldn't expect to be able to like visualize or like tell a straightforward story, one might expect that at least at a sort of structural level or structural or mathematical level, you would be able to understand what's going on. And I think with the measurement problem, even like structurally and mathematically, there's a kind of something missing there. So I think that the inability to visualize is part of the problem, and perhaps makes it more difficult for us to just like think about. But I don't think that's the whole problem. I think there is something missing that is not just that we can't straightforwardly conceptualize or visualize it.
Why can I ask, just why have you completely given up hope on the fact that we'll be able to visualize the quantum world?
Why have I not given up hope?
Or why have you given it? It sounds like you've given up hope that it's even something that is possible, 1,000 years from now.
I don't want to rule anything out. I do think that our brains and our conceptual schemes are very well adapted to the regime in which we actually live, this classical regime, and there's no reason to think that whatever is going on in regimes very far from that will be similar to that in any way. And I do think that, I think the feeling or desire to be able to visualize and conceptualize in a straightforward way, I think that has a tendency to lead people astray a little bit. The sort of expectation that the quantum world must have features that must be comprehensible in a sort of straightforward way. And I
guess I'm curious, why do you think it wouldn't be? Why would some part of the universe be different than? I know this sounds completely stupid, like I sound like a first grader, but why would you expect that what's happening at a small scale would be fundamentally different in its causality than what's happening in the room right now? Why is that? I understand that it's difficult to visualize and it's difficult to prove, and nobody has succeeded, in any public sense in providing that kind of picture of what's happening at the scale of the atom.
Yeah.
But why is it so? Why is there no hope that can be done?
Well, again, I don't want to rule anything out. So I'm not saying that there is no hope, just that I wouldn't necessarily bet on it. In particular, I think you mentioned, for example, causality. And causality is a big part of how we conceptualize the macroscopic world around us. And I think there are very clear and obvious indications that causality in the ordinary sense is something that emerges at macroscopic scales and is just not there at microscopic and submicroscopic scales. There might be other things that are similar to causality, but they're not going to be the same as causation as we understand it and as we interact with it in our immediate surroundings. So that, and similar things can be said about other important elements of the way in which we experience and conceptualize the world. So none of that is to say that we can't know anything about it. We can't make any sense of it. It's just to say that I think we should be wary of expecting that it's going to have certain kinds of classical properties or certain kinds of features that we are familiar with and that we often use in the stories that we tell. It could, but we certainly shouldn't assume that. We shouldn't assume that the microscopic world must have a causal structure. We shouldn't assume that it must have a temporal structure. All of those things could be there, but there are at least some reasons to think that they might not be.
Can I just can I push on this a little bit harder? Yes. I hope I'm not making you uncomfortable.
No.
But why wouldn't we just assume that there is a causal structure, but we're missing some piece of the picture? We're not our devices for which we're inferring all of the information that we have are just not adequate for bringing in the full story. And so what if we see something that looks like it doesn't have a causal tree to it, we just can't see the trunk or something? Wouldn't that be a little more sane than assuming that physics or reality doesn't unfold in this rational conception that we use on a daily basis? I have such a hard. Maybe you can help me understand why it's more appealing to assume for most of these quantum physicists that reality becomes somehow Alice in Wonderland like, as opposed to we're missing some pieces of the picture to have it conform to our everyday understanding of reality?
Well, I think certainly there are people who are trying to make microscopic reality look more classical. That's what I would say the De Broglie people in particular are trying to do. There are just sort of technical reasons, as we have discussed, to think that probably is not going to work. But more generally, I think, chairs and tables are also a very important aspect of our microscopic experience. I'm currently using a chair, as are you. They're very common, they're very important, but nobody would expect that chairs are going to be found in like the quantum regime. And I think for me, causation is very similar. Causation is a type of structure which emerges in macroscopic regimes. It's obviously a very important part of our reality. But there are very sort of clear reasons to think that it is not the kind of thing which exists in its standard form at microscopic scales. And I sort of think, why should it? There are many things which exist at macroscopic scales which don't exist at microscopic scales. There are many emergent structures that we have that we deal with in our lives that are just clearly not going to be there at microscopic scales. It's not obvious to me that causation specifically is any different from those other kinds of things that emerge at macroscopic scales and aren't there at microscopic scales.
But isn't like isn't the whole project of Enlightenment, like post Renaissance, post Enlightenment science, isn't the whole point to provide rational causative explanations for phenomena that don't invoke supernatural things that can't be understood? I mean, isn't that the whole point? Isn't that what distinguishes science from supernaturalism or mysticism or something like that? I mean, what are we doing if we're not trying to provide rational causal explanations for phenomena?
I mean, I definitely think the project is to provide explanations and to understand what is going on through the lens of a physical theory. I just think it's a mistake to presuppose that the physical theory must have some particular kind of structure that must look at a certain way. There's no guarantee that the world must have an underlying causal structure. And yet I would like to think that even if it doesn't have an underlying causal structure, it is still going to be possible for us to understand something of what's happening and what's going on there. And that explanation might look different to the kinds that we are used to. It might be, unfamiliar and take some time to get used to. That doesn't mean that it's, irrational or like supernatural or anything. It just means that it's a different type of structure that's not quite the same as what we're used to in the macroscopic world.
But like, what would you call it if something happened in the room right now? I don't know, something happened and the answer was that it doesn't have a cause to it. Like, wouldn't that be supernaturalism?
Well, hold on. I want to add something to this. I think that what the frame is that things at the very, very small scale are somehow different. They're different than these macroscopic objects because you would not describe the speaker with a wave function. The speaker is an object with length, width, height, location, whatever. And so it doesn't have this potentiality. And technically, I think that if you cross your eyes and blur your vision, you actually could see the speaker as being described by some kind of wave function in terms of, will I move it? Will a fire destroy it? Will there be an earthquake? There is a set of like weird things that could happen to it that you probably could use to describe it. Okay, fine. But if you look at the super, super small scale, we seem to only be able to talk about that world in terms of these probabilistic things, and so causality starts to become weird. But the problem arises, I think, when you have...
So is that because causality and probability don't go together very well?
That's a good question. Is that why?
Like you don't give deterministic answers with a probabilistic statement. Like
are we just using causality in a weird way where really when we say that causality isn't a thing, it's that we're describing a probabilistic system and causal systems have determined outcomes?
I mean, I think that certainly the way that causation is used in philosophy does not exclude probabilistic systems. The causal modeling framework is one way of thinking about causation, and it identifies causation in terms of X causes Y if X in some way changes the probability of Y, and it's or sufficiently so. So in that sense, it doesn't have to be a deterministic influence. It can be a probabilistic influence. I think specifically one of the main problems for positing causation at the microscopic level is not the probabilistic nature, but is the symmetry that doesn't, causation is understood naturally. Our normal understanding of causation requires that there's an asymmetry, that X causes Y and Y doesn't cause X. And that kind of asymmetric relation is very hard to find in the microscopic regime. Everything seems to be sort of time symmetric. There doesn't seem to be the right kind of structure to support an asymmetric causal story. So maybe there's something that I think there probably is some kind of structure there, which is a bit like a generalization of causation, but just doesn't necessarily have all the features that we would normally expect, and in particular doesn't have the sort of asymmetry of causation.
Yeah, it seems like network effects might be indistinguishable from something like that. If you had the collaboration of an almost untraceable number of actors in a scene, it would be really hard to place the starting point of some action at any particular point, perhaps.
And if all the actors are roughly on the same scale, like even if we're talking about let's cut it at the level of atoms. Like, yeah, you have maybe like 100x size difference, or like, but it's not huge. We're not talking of like orders and orders and orders of magnitudes, and so it's different than the context in which we think about it on the large scale. Is that kind of part of it?
Yeah, I think that that definitely, if you look at a sort of microscopic description of things, for sure there are meaningful, substantive, robust connections between things. It's not like there's no structure, but the kind of structure that there is does not seem to lend itself to telling a sort of straightforward branching causal story in the way that we would in the macroscopic world. But I don't think that means we can't explain it or understand it, or that it's beyond comprehension. It just means that we're going to need different tools to what we might use in describing macroscopic reality.
There is this other problem, which is that if causality is something that only emerges at a certain point, then doesn't it become something that you have to draw in by hand? Where you say, here's the place where causality begins. Prior to this, we do not have causality. And then all of a sudden you have to create a mechanism for it. Like, doesn't that create more problems than it solves?
It's like the Heisenberg gap or something?
Yeah.
I think that the story I would want to tell about the emergence of causality is not that there is a sharp cutoff, but that there is a kind of gradient from nothing asymmetric causal at all towards very strong asymmetries, causal structures in the macroscopic world, and then in between you're going to have sort of things moving in degrees. It is in effect, it's kind of an effect of scale. It's the effect of averaging over large numbers of particles. So the more particles you have, the more sort of strong asymmetries you're going to end up sort of being able to see. So from that point of view, it's not like the Heisenberg cut, because the Heisenberg cut does seem like it needs to be kind of precise and clear and appear at one particular point, whereas the emergence of causation, it seems to me, is something that could perfectly well happen in degrees.
And so basically, like, as systems tend towards being, is this a size thing? Like, they get to be sufficiently large? Or, because it doesn't seem to be necessarily about complexity, because you could have a bunch of quantum objects that are not causal yet.
Yeah, I mean, roughly speaking, it seems to me that causation is very closely tied to thermodynamics, the second law of thermodynamics in particular. And the second law of thermodynamics does not really apply for like individual microscopic particles. The second law of thermodynamics comes from averaging over sufficiently large numbers of particles. So that suggests to me that you're only going to be able to get things that look like causation in the sense that we understand it once you get into the kinds of regimes where thermodynamics is an appropriate description of the system.
There's also this other thing that keeps kind of floating around in my head, which is the fact that there are weird probabilistic features of nature, things that follow normal distributions.
Yeah.
And that's such a profound mystery as to why that occurs. And I feel like it somehow mirrors some kind of process that maybe happens at this micro scale that we're talking about, because it is very strange that I don't know if you've seen this demonstration where you can take a a bunch of little marbles and then run them through a field of pegs.
Yeah.
And then they end up providing a normal distribution as they filter into these bins at the bottom.
Yeah.
And that I have no language for being able to map that significantly onto something that's happening in the quantum realm. And yet I see that. And my immediate thought is that is somehow vital to understanding these systems that we can't quite see.
No, I think that intuition is right, because I think what those types of experiments are demonstrating is the role of symmetries. I think the solution space you get at the end is strongly constrained by the symmetries of the system, such that it doesn't matter too much what the initial state is, because the symmetries result in kind of sorting into certain kinds of final states. And I think you're very right to identify that as being relevant, because it's certainly true that in the microscopic world, the role of symmetries becomes increasingly important in understanding what kinds of solutions are possible, and also what kinds of things can even be physically real in the first place. So that kind of mapping is I think a good way of thinking about the fact that the symmetries that systems are subject to perhaps play more of a role than we immediately understand in shaping what the solution space looks like and what possible states are.
So, and then another question that I kind of have is whether or not a mathematical intuition is the proper first intuition to develop about a system. Like, I think about something, I've been reading this book about the history of digital imagery. It's called A Brief History of the Pixel.
Yeah.
And the beginning of the book talks about Fourier and Fourier transforms, and Fourier's realization that you could take a complex wave and you could basically treat it in a very specific way that allowed you to provide a very compressed set of information that described something very, very complex.
Yeah.
But that is in terms of our attempts to understand the world and understand how information is transmitted through the world and how a visual field offers some kind of cohesive picture, like that's very late in the game. I think that you can point to painting and sculpture and all of the studies of vibrating strings and the entire history of mathematics as being the thing that finally ends on this dramatic moment where Fourier is like, hey, wait a second, this is actually, there's a different way of seeing this.
Yeah.
But he couldn't have gotten there without everything that preceded it. And so I wonder sometimes when it comes to quantum mechanics, if taking this incredibly complicated feature of nature that we have no real visual intuition for and treating it exclusively with mathematics, like, are we screwing ourselves? Are we preventing ourselves from being able to get something that is more powerful than just math alone?
Yeah, no, I feel the force of that intuition for sure. I guess I think people, it's not obvious what the alternative is, because the only access it seems like we have, at least right now, to these kinds of things are via the mathematical structure of the theory we have, which predicts certain measurement outcomes. We're never going to have direct visual interactions with them. We're never going to have any other kind of interaction other than sort of inferring them from the observed measurement outcomes. And so it seems very hard right now to divorce whatever is there from the mathematical framework that we use to predict the measurement outcomes, because that's all we have to characterize it right now. So I mean, yes, I think it would be good to have an alternative, but I'm not quite sure how you get there, given that the math is so central to our understanding of what it is and our reasons for thinking that there is any such thing.
Well, there's this really weird thing about, and it would be interesting to get your perspective on this. So at some point, I was trying to trace out the parameterization of spin. So, like, electrons are supposed to have spin 1/2, and spin 1/2 is this strange feature that doesn't map neatly onto physical reality.
Yeah.
And one of the consequences of this strange angular momentum of the electron is that there's it has a weird gyromagnetic factor. It has a gyromagnetic factor of 2 as opposed to 1. And so I've mentioned this briefly on the podcast, just to make sure that I have this correct. It's basically that a classical charged particle in orbit should have this direct relationship between its charge to mass and the strength of the magnet that it produces as it orbits and its angular momentum. So it's this kind of, is that accurate? Okay. For sure. I'm reading about this, and so I'm trying to piece it together. And so there's this prediction, because they have no idea what the electron is. They're like, maybe it's in orbit, maybe it's not in orbit, maybe it's doing something different. And so Larmor comes up with this relationship for a classical particle. And then they go and they test it. And the test is, it's Einstein and this guy whose name is Wander de Haas, which is one of the most incredible names that I've come across in all of physics.
I've never heard that before.
And they do this test, and they come up with a classical ratio. Because what they do is they take an iron bar, they suspend it inside of a solenoid, and they pulse current through the solenoid, and then they see how the bar rotates. Because they basically are like, well, look, we can't measure a single electron. We can measure the electrons in the entire bar in bulk, and then based off of the strength of the magnetic field and how much it twists, we'll be able to determine what that ratio is. They do the experiment, they determine the ratio is 1. And obviously, later it turns out to be that it's not. It has this other weird ratio. And the reason their experiment fails is because the Earth's magnetic field is sufficiently strong to affect the turning of the bar, and so you have to build like a Faraday cage. As is the case for most of these esoteric experiments, it's difficult to do. But I'm like, there is a feature of nature that is this weird gyromagnetic ratio where the bar actually does rotate more than you would expect. So how do you have a macroscopic feature of a quantum phenomenon that is not supposed to have a physical basis? That's the part that keeps me up at night, where I'm like, okay, so spin is not supposed to be a physical characteristic of the electron. And yet if you put this bar inside of the solenoid and you make all of the electrons spin in the same direction all at once, you can measure the way that it deflects the bar, despite the fact that it's not a physical characteristic.
I mean, I think I would not say that spin is not a physical characteristic. What I would say is that whatever spin is not a thing that we can straightforwardly analogize to a thing that we experience in the macroscopic world. It's a well-defined property of the electron. It has well-defined mathematical characterizations. We know the effect that it has in various kinds of interactions and so on. We just don't have, I think, a visualization or a clear story about what it is that we can straightforwardly make an analogy to the macroscopic world. But it is a real thing. And so in that sense, when you aggregate enough electrons and you put together these real properties, these properties add up to something that is more sort of macroscopically familiar. But yes, there is something a bit strange about, and perhaps that we'd like to understand better about how exactly real properties of the kind that we interact with are supposed to emerge out of the mathematized properties that quantum particles have. And we have some ideas about how that works, but I think the full story about the emergence of classical reality and our perspective on it is not fully clear. And the kind of problem you raise is sort of part of that in terms of converting from what seems a very mathematical picture to a more physical picture.
Do you think that the measurement problem is kind of an entry point to that project?
Yes, I do. It seems to me that the measurement problem is indicating that there are some limitations in our understanding of the nature of our perspective on the world and the way in which our experience kind of latches onto physical reality. I suspect that there's something that we haven't understood correctly about that, or something that we haven't gotten right about that. So if I'm right, then yes, those things are connected. On the other hand, there are some proposed solutions where there doesn't seem to be that much of a connection. So sort of there's a bit unresolved right now because we don't know what the right solution is. But for me personally, it does seem correct to say that there are good indications that the role of perspectives and the way in which we interact with the world is going to be very, very relevant there.
All right, should we talk a bit about your proposed revision to our quantum epistemology? I gathered from looking over your book that you think there should be more coherence between the different elements of the way that we approach these quantum systems. So our pre-existing theories, our beliefs about how the measurement systems operate, the devices, uh, the outcomes, how those are interpreted, and our pre-existing background scientific beliefs. And
Yeah,
then there's some sort of feedback between all of these that you see as being progressive if
yeah.
we are to encounter any particular piece of this puzzle with all of these in mind. Could you help us understand that a little bit better?
So this is a sort of progressive coherentist approach essentially. I mean, the thought is that we start off doing science and we start off with some sort of loosely defined assumptions about the nature of what we're doing, the reliability of what we're doing, the fact that there's a world out there that we're interacting with, and our measurements are giving us information. Um, and at that sort of that stage, we don't necessarily know exactly what the measurement is doing. We don't necessarily know exactly what it's interacting with. Everything is quite sort of vaguely defined. But the expectation is that as we go forward and develop our scientific theory, one of the things the theory will do is tell us what the measurement is doing, what our measurement instruments are accessing, and how they interact with the world, and that they'll have some kind of story to tell. And so the expectation that we have, I think, is that as we go on and that story becomes more precise and clear, that story should, at least in large part, affirm the original assumptions we made about the reliability of our means of inquiry, the fact that we are really accessing the things we think we're accessing, that we're really getting information. So there's a sort of expectation of coherence, not just at a single time, but in terms of the way that we have arrived at our conclusions and the way we have built up our views over time. In particular, when you look at something like quantum mechanics, to do quantum mechanics, to make any of the observations that we make in quantum mechanics, you must invoke a whole bunch of other theories. You must assume that in the classical regime, your measuring devices are doing the things you expect. You're going to have to assume that the electricity that you're using to power the devices is working in certain ways. You're going to have to be appealing to theories of classical optics to understand the ways in which the mirrors and lenses are working, and all these things. So there's a whole bunch of pre-existing scientific knowledge that goes into doing a quantum experiment. So in order to sort of have a coherent story at the end, you need to be the case that whatever picture you ultimately arrive at of the quantum world is able to reproduce and affirm, at least roughly speaking, the correctness of all the scientific knowledge that you used to do those tests in the first place. Otherwise, the whole thing is just not coherent with itself and falls down. So that's the kind of epistemology that I'm sort of trying to drive at, that whatever happens in the long run, our story about quantum mechanics needs to support a sensible account of the way in which we arrived at it and the way in which other pre-existing scientific knowledge fit into that.
And can new information feed forward and backwards in this coherence? Like, is it possible you learn something that changes the way that you understand your electricity and therefore changes the entire path of the knowledge from the device all the way to the phenomenon at the heart that you're studying?
Yes, I do think for sure, in particular, as you start out with often quite vague assumptions about how things work, and as you go on and do your theory, those assumptions get made more precise and more clear, and you perhaps understand in a much more concrete sense what is going on. So in that sense, your prior knowledge is being you're getting feedback from the more quantitative theory that you arrive at, and that's helping you understand that better. And certainly, I think it's possible to some degree that what you learn when you do your more complex science changes in some ways your understanding of what was going on in the classical regime or at the simpler level. I think that is fine. What is important, though, is to, I think, look in some detail and carefully at the nature of the story you're left with at the end. Some amount of changes is fine, and we shouldn't be closed off to it, but we still want to make sure that the result at the end, you can still understand in a sort of holistic way how it's possible to gain the kind of knowledge we're supposed to be getting to support the theory that we're talking about. anyway, and so I think it's not a sort of straightforward prescription. It's not a case, we should never be able to change any pre-existing knowledge. It's a somewhat more complicated picture in which, as we improve and adjust our more advanced scientific knowledge, we have to sort of understand how that fits together with our earlier scientific knowledge and ensure that things are being mutually adjusted in ways that remain consistent with each other.
So while Shiloh formulates his next question, I wonder if we can return to something we touched on earlier, which is the outsized influence that quantum mechanics has on basically everything from psychology to biology to, I'm waiting for some kind of quantum theory of economics to drop at any moment, or archaeology. In some ways, it's very strange to me that this deeply esoteric regime that, for all intents and purposes, collapses to something classical and predictable and causal by the time that any of us come around to it, has such a powerful grip on psychology of so many people across so much time. What is that? Why do you think that is?
I think part of it is understanding quantum mechanics, understanding what it is, has required us to introduce a whole bunch of new concepts and new ideas and new ways of thinking about the world. We've been forced into this by the theory being so weird. And concepts are useful. Concepts give us new ways to think about things, new ways to conceptualize things. And so not always, but certainly sometimes, even if you're working in a regime where quantum mechanics, the physical theory, is not really relevant, nonetheless, it's entirely possible that some of the conceptual stuff that has come out of quantum mechanics could still be a useful way to conceptualize whatever's going on in that regime, because the concepts and ideas are somewhat distinct from the theory itself. So if you're talking about quantum contextuality, if you're talking about entanglement, non-locality, even if it's in some other domain, those things are not literally physically present in the same sense that they are in quantum mechanics. Nonetheless, it's possible that the sort of ideas could be a useful conceptual framework for you to be using in some sense.
And do you think that it does actually travel in that way? Or do you think that because it's hard for me to not see the emergence of postmodernism, the sense that nothing really causes anything, everything just happens, and it's
extremely permissive. It's an extremely permissive approach to reality, right? It seems like, I think that's why you see the proliferation of the word quantum in every single domain at this point, because it basically just means
weird stuff happens, we can't explain it.
I don't have to make sense. I'm going to throw this factor out, and it's quantum. So,
I have some bias there, because I am not inclined to interpret even quantum mechanics itself in that way. I am also not pro the sort of permissive, it's too weird to understand anything goes approach to quantum mechanics either. So I think I perhaps see it as a more concrete and physically grounded thing than some other people might. I would agree with you that one wants to be careful about taking ideas from quantum mechanics and applying them in other fields. Certainly there are some cases where maybe that just looks like a buzzword that's being used without any true grounding. But I do think there are cases where specific elements of the conceptual framework are more general and can be translated. And so there are certainly some applications where that looks more reasonable. You have to be using it not just for the sake of using it, but because there is really some genuine conceptual ground to be covered with it.
How did you come to see the world this way? Because most of the people that we talk to that spend a lot of time thinking about quantum physics, except for a very small handful of them, are really happy for it to be magical and weird and impossible to make sense of. And so you have a unique frame. How did you get there?
I think it is related to these concerns about epistemology that we've been discussing, because a lot of the magical weird approaches seem to have these kinds of troubling consequences where, everybody has their own facts and they're not connected, or there are no facts, or all of these kinds of things. I find it really hard to combine those claims with a sensible story about the kinds of processes that are involved in actually doing science. I think seeing someone say something like quantum mechanics proves there is no reality or something, I just think that can't be right. No scientific theory could prove that, because it's a presupposition of the process of doing science that there is a reality. And so if the result of your scientific inquiry is, oh, there's no reality, all you've done is just shown that there was some inconsistency in your process somewhere. So that kind of claim just seems to me too extreme to possibly ever be justified by any scientific theory. So I think that what we get once we start thinking seriously about what is required to make sense of the process of doing science is a picture in which a certain degree of concreteness and specificity must be there in order for science to make any sense of it as an endeavor at all. And for sure, it could be weird. The world could be very strange and very unlike what we expect. But, I think it seems to me that there need to be some kind of facts and some kind of shared facts and some kind of standpoint on which we can, from which we can start in order to be able to do science.
What do you think is the distribution between the number of people that are studying, I don't want to say the philosophy of quantum physics, but study quantum physics as a theoretical discipline, versus the people that are really in the laboratory trying to put together experiments that test some of these theoretical predictions?
I'm not completely sure of the numbers. I think I would say the majority of working physicists are somewhat more focused on practical problems, or problems that you might think would eventually have a practical application. In large part because of reasons of funding and so on. It's obviously easier to get funding for projects that have an obvious practical application. Certainly the parts of physics which deal very specifically with the conceptual issues, and quantum foundations in particular is perhaps the most obvious example, are much smaller than the rest of physics and less well funded, and certainly less well known and less popular. But I do think that many physicists who officially work in other parts of physics nonetheless have an interest in this stuff and may do some of it on the side and may contribute nonetheless. It's the number of people who are officially full-time quantum foundations people is quite small, but many people from outside of that group will still contribute and be part of that.
That's really interesting. I'm asking so we've been working our way through this history of physics, and there seems to be a really clear transition towards mathematics roughly around the time of Pauli and Dirac and Heisenberg and Schrödinger, where they have an equation that tells them something deeply fundamental about nature, and there's just not very many experimentalists around. I came across this funny story where the Stern-Gerlach experiment was somehow Bohr was involved in the theoretical discussion of it, and then and he was doing it with Gerlach, who was also the theorist, and then they found Stern, and Stern was the experimentalist, and they were like, "Thank God, finally we have someone who can actually build us an apparatus." And I wonder if there isn't some element of quantum theory and the fundamentals of quantum physics that aren't waylaid by the fact that making experiments that actually really, I don't want to say challenge, but maybe refine the way that the theory is packaged are fewer and farther between than we would like. Is that totally unreasonable, or do you think that there's plenty of people that are doing extraordinary experiments that just continuously keep verifying that everything is copacetic?
Yes. Well, I think quantum mechanics has been very well tested in the regimes which are straightforwardly accessible to experiment with the technology that we currently have. I think it's certainly not that there's unwillingness to do experiments which would challenge it, but it's not very easy to formulate such experiments that can actually be done. There's two main directions in which you might expect it to be challenged experimentally. And one is going down and looking at things at very small scales, for which you need a particle accelerator. And obviously those are very expensive. There are very strong limitations on the extent to which we can go further and further in that direction. And the other direction that's really interesting to me at the moment is sort of tabletop experiments for quantum gravity. So various experiments hoping to sort of probe the interactions between quantum mechanics and gravity, and to probably demonstrate that gravity is quantum mechanical in nature, and maybe learn something about exactly how it is quantum mechanical in nature. Those, I think, are perhaps more realistic to happen in the short term. There's still a lot of technical challenges with doing that. It's not easy to do, but that is a thing that can be done perhaps with less expensive equipment, without building a particle accelerator. So that there's some really interesting stuff going on there that I'm excited to see the outcomes of it. But there too, it is certainly very challenging. So I don't think it's a lack of willingness. It's just a lack of. It's difficult to find new experiments that we can actually do, which would push the theory in these ways.
Mm-hmm.
Just to circle back, I was processing when you were describing the progressive coherentism epistemology. Can you just lay out side by side how this differs from the traditional epistemology for quantum mechanics, just so I can have something in my head to walk away with to compare these two different approaches, so I understand one versus the other? Like maybe even give an example or something of how maybe some piece of the puzzle was put together using the previous epistemology, but maybe how we might look at it differently going forward.
Yes. Well, I think part of the problem is that I think discussions of the measurement problem just have not focused on epistemology very much. There has not been a primary concern in most discussions of it. So in particular, I think there has been a sort of long-standing assumption that that in effect there's kind of a one-to-one map between here is a mathematical theory, here are the observations which provide confirmation for it. And regardless of how you interpret the theory, the same observations will always provide confirmation for it. You don't therefore have to worry about whether your interpretation is sort of consistent at the epistemic level, because just by default, it's the same mathematical theory. It in some sense makes the same predictions, so it is confirmed by the same things. Which is kind of along the lines of the way in which some philosophers at various times have thought about confirmation. It's sort of reminiscent to me of logical positivism, for example, the thought that like every sentence can just be mapped one-to-one to a verification process, and that's it. And so if you're thinking about confirmation in that way, then it does, I think, seem natural to not be too worried about the epistemology and just assume it will all work out. I think the story I want to tell is perhaps more influenced by a more sort of holistic, coherentist approach to epistemology, in which we sort of appreciate that when you make an observation, its significance in terms of what it does or does not confirm relies on a whole bunch of other background assumptions, and all of these things are linked together in very tight, complex ways. And so if you change the interpretation of the theory, there's no guarantee that the same observations still support the theory, because you've messed with all of the supporting assumptions, and so the story might just not work out any longer. And so I think once you start thinking in that more sort of holistic, connected way, you start to see that these interpretations can lead to significant epistemic problems, and in virtue of like disrupting the relation we expect to have between the evidence and the theory.
I see. So like maybe an example would be if I assume that photons are little magic bowling ball thingies, and I shoot one of them at a time with my gun, and it seems like it interferes with itself, then both of these bowling balls must have gone through two different slits at once in this experiment. Whereas if I'm like, okay, what is my actual system measuring? It's measuring these interference patterns. And what is my photon gun thingy doing? Well, it's basically a power threshold for the emission of photons. And so I'm starting to think about the whole system in terms of the interpretation of what's happening in a more coherent fashion that's not just like bringing the baggage of what I thought I was doing in the first place to the table.
The approach that I think has traditionally been taken is you posit your interpretation of quantum mechanics, and then you prove that it is, in some sense, like empirically equivalent to standard quantum mechanics. You show that like in some mathematical sense, it makes the same predictions as standard quantum mechanics for experiments. And the thought is that then you're done. These theories are the same empirically. They must be equally confirmed. That's the end of the story. Whereas I think what I want to say is that empirical equivalence itself is a sort of complicated notion. This is not a thing that you can really establish by some sort of bare mathematical mapping between your interpretation and the theory. You really need to kind of sort of understand the full story about what your interpretation is actually saying about the nature of the processes that are involved and the nature and way these things are related. In the Everett interpretation, it's not enough for me to just say, oh, well, the mod squared amplitudes are there in the theory and I can make a mapping between amplitudes and probabilities. So done, we're sorted. You really need to be able to tell some story about what probability would mean and how this could possibly tie into our experience in a way that would confirm the theory. Similarly, in the sort of relational perspectival interpretations, it's not enough, I think, to just postulate that each observer is going to see the observations that we would expect given quantum mechanics. You also need to be able to tell some story about how observers could gain information about this, how observers could actually come to like justifiably believe that other observers are seeing similar things and so on. So I think that my concern is with this, I think, overly simplistic approach to epistemology, which says as long as you've proved empirical equivalence in like some sense, you're done. There's no further problem. I think that we do need to understand the whole picture and the way all these things relate to each other.
I love that. Do you think that that's gonna? I guess this is my last point. Do you think that ties into other sciences as well, or is this sort of epistemological revision limited to something like quantum physics or physics itself?
Yes, for sure. I mean, the progressive coherentist idea that I am thinking about there is influenced by a variety of people, particularly Ha-Seok Chang, and that idea was originally developed as a description of scientific knowledge in general, not just in some particular regime. And I think Chang is right to say this is the sort of structure of the growth of scientific knowledge, that we start out with these assumptions that slowly get made more precise and clear over time. What I think is novel about quantum mechanics is that the measurement problem to me looks like an instance where, at least on the face of it, the theory we arrive at fails to affirm the assumptions that we started out with in the way that you expect, in a way that I can't think of many other examples in other parts of science where there's been what looks like a significant undermining of the sort of basic epistemological assumptions.
Maybe the Ptolemaic astronomers are the closest thing you could come to, right? Which is like also this incredibly mathematically rigorous description of observations and a very broad, highly articulate data set, but the sort of baggage that's brought to the table restricts the accurate perspective of the whole picture at some point.
Yeah, definitely there was sort of complexity in there in terms of the way in which the data was being interpreted. I think that even there in that case, though, for sure there were very significant revisions that had to be made to the way in which they understood the nature of the world and their place in it. But none of those revisions, I think, sort of undermined the basic founding assumptions about the possibility of doing science, the possibility of communicating with other observers, the possibility of using observations to learn about the structure of the world. And so I think that's the thing that is for me novel about quantum mechanics specifically, is that at least on the face of it, it looks like there's this kind of undermining problem. And I am optimistic that, as a matter of fact, the true solution will not undermine all of these things and it will all work out. But I think it is, it's notable and distinctive that several very prominent interpretations of quantum mechanics do really kind of mess with this kind of progressive structure and failed to do what we expect in terms of the affirming of the original assumptions.
Yeah, I mean, it could be as simple as technological advancement. Some technology we can't even imagine. Most technologies are unimaginable until they happen.
Mm-hmm.
And I think in some sense with the Ptolemaic situation, it may have been, I mean, obviously there was competing theories at the time, but there was a technological lever that occurred, right? The telescope appeared, eventually space exploration appeared. So like there could be some sort of dare I say, quantum leap in our technological ability to
Well, I mean, the
yes.
Copernican revolution, it was several different things coming together at once, because that change in understanding was not possible without also various changes in our understanding of like force and motion and the way in what is the natural state of motion, and so all of those things from several different parts of physics kind of converged on that new understanding and the Copernican model, and seeing why the Copernican model was right. So I think it's I think the same is very likely going to happen here. I think it's very likely that ideas, certainly from general and special relativity and from quantum gravity, will feed back into our understanding of the measurement problem, and will perhaps give us new ideas about how to move forward with that. So I would hope that it would be a sort of similar thing where you're getting some convergence of ideas from different parts of physics.
Isn't one of the main places where that convergence can come from today trying to figure out what mass is? Because I think that there's from all of the reading that I've done, it seems like there's this weird break in physics because mass is the starting assumption of almost every presentation.
Mm-hmm.
And so if you're dealing with gravity, if you're dealing with general relativity, you're dealing already with this concept of mass that does something in the world. Like we had a friend who made he made a funny observation where he was like, it's weird that when you see these pop sci representations of bent spacetime, it's a trampoline that a bowling ball is pressing down. But no one's really asking the question of like what gives the bowling ball that power in the first place. It's just treated as a starting assumption.
Mm-hmm.
And it seems impossible to be able to explain let's say even the equivalence principle. Like why is inertia so similar to gravitational force, but like almost pulling in opposite directions? Like if you think about the hammer drop, dropping the hammer and the feather at the same time on the moon or in a vacuum, like they fall at the same speed. And that's insane.
Mm-hmm.
And like you just at some point you look at it and you're like, oh, okay, obviously.
Are you just trying to say there's like fundamental concepts at the heart of
I literally think that
bottlenecks almost?
I think that so Emily said something interesting where she was like, there was a piece of the Copernican revolution where we started to understand the mechanics of forces in a new and different way, which allowed us to cast our gaze onto the cosmos and see something in a different way.
Yeah.
And now we're on this precipice of trying to understand quantum theories and how quantum theories interface with the larger systems. And I'm like, hey, I think that understanding what mass is at the heart of this next step, because how do you answer the question of what causes quantum gravity if you cannot ask the question or answer the question of where does mass come from? Like what makes them, and not in the sense of there are strong forces, there are weak forces, and they attract each other, but literally this like very physical question of what is mass? Like that seems like the key for the future.
Yeah, I sort of agree. I guess I don't know exactly what the right question is to ask. I do think there's some significant conceptual question that we probably haven't understood correctly. And in particular, I share the intuition that it is probably something to do with relativity and space-time, and how those things interface with quantum mechanics. Certainly, I think there's various interesting insights from relativity in terms of how we should think about observables and symmetries and what is physically real. That seems to me very relevant to how we should think about quantum mechanics too. And I don't quite know how that story is going to go in the future, but I do agree that for sure that some conceptual stuff from relativity is probably going to have to be translated across to quantum mechanics to make that story work.
Yeah, I mean, it's interesting how far along it feels like we are, and yet how far there still feels like we have to go in order to be able to have this coherent picture of nature.
Mm-hmm. Yeah.
Do you think that you're going to spend your time working on the measurement problem, or do you have something else that you're preoccupied with now that you've finished the book?
I certainly still think about the measurement problem. More generally, I've been thinking a lot recently about relational descriptions in physics, both in quantum mechanics and in relativity, and I guess a little bit in quantum gravity, and trying to make sense of that kind of story. Also, I've been increasingly interested in questions related to emergence, in particular. This is in combination with thinking about relational interpretations of quantum mechanics. I think there comes along a worry that the quantum formalism that we have is maybe only suitable to describe a relation to a macroscopic system. And so that seems to raise problems for emergence, because you might naturally expect that we would want to be able to start from a description which doesn't include any macroscopic systems and then build up in a way that arrives at the macroscopic systems. But if quantum mechanics itself is only suited to describe things relative to macroscopic systems, it looks like some other formalism beyond quantum mechanics would be needed to do that. So I've been interested recently in thinking about that and in how it interfaces with the measurement problem, and also with these kinds of concerns about relativity and relational observables.
And do you take purely a theoretical approach to this, or do you also collaborate with experimentalists or conduct your own experiments? Like, how does that work?
I just do theory at the moment, yeah.
Very cool. I mean, there's a lot of ideas that are on the table here. I
really appreciate your optimism about the idea that, yeah, there's holes in all of this, but there is a sign pointing forward about how we might one day reconcile a lot of these issues.
Well, I think the fact that there are these problems is in a way quite positive, because I think the picture that we had was there are all these solutions and they're all equally good, and how we could we possibly know there's no choice? And I think that's not the situation. I think the fact that there are many problems means that when we know the right answer, we'll know it, because we'll see that this is the thing which does fix all of the problems and does have all the properties we need. So I feel optimistic, at least, that when someone eventually figures out what the solution is it will be quite clear that it's the right solution.
I like that.
I like that as well. I think that this is a really powerful frame for looking at the world, because there is this great tragedy that has emerged from the strangeness of quantum physics, which is that it threatens to topple our ability to say anything with any certainty about the world.
Yeah.
And what I really value about the work that you're doing is that you're saying, well, hold on a second. That seems probably like maybe not the best way of looking at this, and maybe we don't have to give up on the entire project. And it seems like there's not very many people who are saying that. And
yeah, I wish there would be more people saying that. But yes, no, I think for sure, I don't want to understate the weirdness of quantum mechanics. I think for sure something very strange is going on there. But I do think that in order to be consistent, in order for the project of science to make sense, we have to maintain that there is something going on there, and it's something that we can potentially describe and explain, even if it ends up looking very strange.
Do people tend to appreciate what you do, or do they get combative? Like, what has the reception been among quantum physicists?
I think that there's variation. I mean, some quantum physicists are just not, of the sort of more physicsy end, are just not very interested in the interpretative stuff, which is obviously that's fine. That's their prerogative. Of those who are interested, I think some people are quite defensive of their existing preferred interpretation and wanting to defend it. But I think there's also been a good degree of openness and willingness to investigate new things. I think there's interesting developments in quantum foundations recently related to these kinds of perspectival and relational ideas, and so if people, I think, are interested and excited by that kind of project, so there's definitely a lot of sort of forward motion in that sense.
Did you know when you were little that this is what you were going to do with your life?
I did always say I was going to be a scientist, so yes, more or less that's what I've done.
Very nice.
Well, yeah, I guess we'll let you get back to the science then. I'm curious to see what comes from your pen next. It'll be this has been an interesting piece of the puzzle for us, and I really appreciate the work you're doing.
Thank you so much. This was really fun.
We'll let you go. Have a great rest of your day, Emily. Thank you so much. Bye, everybody.